All right, chapter 7 is dealing with a major concept in statistics called sampling distributions. This is going to be kind of the foundation of all of our future tests and analysis that we're going to be doing in semester 2. So how are parameters and statistics similar? So hopefully, this is just a little review about whether you remember what these words kind of mean. How are they similar? How are they different? Well, if you recall, a statistic is a measure from a sample. Measure taken from sample data. And a parameter is simply a measure taken from population data. So I think this kind of illustrates both how they're similar and how they're different. How are they different? Well, this is taken from sample data, this is taken from population data. How are they similar? Well, they're both measures taken from data. The measure could be the mean, could be the standard deviation, could be the IQR, the median, the minimum, the maximum, Q1. There's literally, many different measures that you can take. But if it's from a sample data, it's a statistic. If it's from population data, it's a parameter. Fill in the symbols for the table to the right. This is just review. For proportions, we use p hat. And for the true population parameter, we use p. For the mean, we use x bar for samples and mu for the population. Standard deviation, we use s and sigma. Those are really the only special notations that we have in statistics, or that I know of, that we use. For everything else, we kind of just say, well, the statistic, we call it the sample median. Or we call it the population median. There's no, again, that I'm aware of, there's no special notation. Same with like IQR or minimums or maximums or Q1s or Q2s. There's no special notation for those that I'm aware of. And this kind of does illustrate that these are the ones we're going to use the most. So those are the special notations. Please be clear about which ones are statistics and which ones are parameters. More definitions. A point estimator and a point estimate. I wish I would have put this in a different order, so I'm going to do this one first. A point estimator is a statistic that provides an estimate for a population parameter. Let's say I want to estimate mu, the true population mean. What would be a sensible statistic that I could use from a sample to estimate this population parameter? Well, hopefully you would think the sample mean would be a good estimator for the population mean. And of course it is. But surprisingly, not all sample statistics, like for example, the sample minimum is not a good estimator for the population minimum. But for the big ones, usually that's the stat that's going to estimate but we just call that a point estimator. So in this case, X bar is a point estimator. A point estimator for mu. Okay? Now a point estimate is just one specific value of that statistic from one sample. So as an example, let's say I take a sample of 30 kids and I calculate the average height, and I get a height of 67 inches. I get a mean of the sample of that. So this one specific value would be a point estimate. So it sounds like these might be the same, but the estimator is the statistic. The actual estimate is like one specific measure from a sample. Okay? Okay, the true mean age of a large group of students is 16.8 years old. Define what true mean means in this case using proper statistic. Well, if we say the true mean, we probably mean that that's the population parameter. That would be the population parameter. That would be the parameter, which would be the population mean, which is mu equals 16.8. So saying true mean, they are probably referring to the actual population mean. Suppose we take a sample of 30 kids from this population. Will the sample be exactly 16.8? Why or why not? Probably not. If the true mean is 16.8, and we take a sample of size 30, we will probably get an X bar that is close to that, but probably not exactly the same as that. Maybe we would get 16.8, I don't know, years old. Who knows what we're going to get, but it's probably going to be slightly different than that. By the way, the X bar is our point estimator. This is our point estimate for the population mean, okay? Why or why not? This would just be sampling variability. Sample to sample variation. Maybe we just get a couple people that are a little bit younger, or a couple people that are a little bit older, or for whatever reason. That's not bias, that's not errors in our sampling technique. This is just random chance variation from sample to sample, assuming we take a good sample. So the value of a statistic will vary in repeated sampling due to random chance. That's sampling variability. We've talked about this all before. We're just trying to kind of formalize it here today. So what is a sampling distribution? This is the important topic. This is the focus of this chapter. The sampling distribution of a statistic is the distribution of values taken by that statistic in all possible samples of the same size from the same population. So I don't know, pause the video and read it 2 or 3 times and try to think about it. But basically, the sampling distribution of a statistic is the distribution of values of that statistic taken in all possible samples of the same size from the same population. I think the best way for me to try to describe it is to show you kind of an example. Now, we did an activity in class, but if you weren't in class, I'm going to kind of just walk you through what we did. It is usually too difficult or time-consuming to take all possible samples of size n to obtain the distribution, the sampling distribution. Therefore, we will use simulations to create partial sampling distributions. I'll try to talk about that here in a little bit. So I used Fathom to simulate this activity we did in class. So here's a distributions of heights from a population. I think we said this was a population, like a class of AP Stat students. Now, I don't know how many I got here. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I don't know. It looks like there's about, I don't know, maybe 40 data points here. Oh, we shouldn't use small n. This is our population size. So I'm just going to say 40. So this is the population distribution. I could ask you, what does each one of these little things represent? Each little dot. This represents one individual in the population, and it represents their height. So this is a height of one person. And this is a collection of all people in the population. That's the population distribution. Now, if we want to estimate the average height, I'm going to take a sample. In reality, we don't have this population distribution. So what we do is we take a sample. So we took a sample of size 4. Here are the individuals in that sample. This is called the sample distribution, or the distribution of a sample. What does each value represent? This represents the height of one individual. Just like the population distribution, each dot represents the height of one person, in this case, one person in the sample. Okay? So what we're going to do with our sample is we're going to calculate the sample mean. And there is a true mean here. I don't know what the true mean is. It looks like it might be, if I did the mean of this distribution, since it's the population, that would be mu. Let's just say it's 69, just for the sake of argument. We're going to take our sample height, our sample mean height. So I don't know what it would be. It'd probably be somewhere maybe right around here. Let's just say maybe it's about 70.5, maybe. And that's our little X bar. That is our point estimate. So what we're going to do is we're going to take that 70.5 and we're going to graph it down here. Right there it is. Then we're going to repeat that process. We're going to take another sample of size 4. We're going to get 4 more points in this graph, a different set of 4 points. We're going to calculate a different sample mean. Maybe that one's 68. And then we're going to plot 68 right there. And then we repeat it again, find another sample. So every single one of these dots is a little X bar, is a sample of size 4 where we calculated the average and plotted it. This one right here is another sample of size 4 where we calculated the sample average and plotted it. This is a sampling distribution. Why? Because it's a collection of sample statistics. In this case, it is the sampling distribution of sample means. It's a collection of X bars. Every point is that. Now, technically, it's just an approximate sampling distribution. The true entire sampling distribution has to have the sample means of all possible samples of size 4. So if I have 40 different people in my population, to do the true sampling distribution, I'd actually have to collect every possible combination of 4 people from the population of 40. By the way, there are a lot of combinations. And choose R 40, 4. There are 91,000 different combinations that we would have to create and find those samples, sample means. So obviously I didn't do all 91,000 combinations of sample size 4 from 40. So we kind of say this is an approximate or a partial sampling distribution or a simulated sampling distribution. But what it does is it gives me an idea of what kind of statistics I will get when I try to estimate the true population parameter. Now I said the true parameter, the true mean was 69. That's like right here. That's the true mean. As you can see, these estimators, these sample means, are going to vary around that true mean. You know, I might get close, I might get lucky, I might get a couple tall people and have an overestimate, or I might have some shorter people and get a quite low estimate for my X bar. When we take our one sample, we don't know which of these dots we're going to get. We don't know if we're really close to the true mean or if we're one of the ones that are further away. But what the sampling distribution is going to help us do, it's going to help us estimate on average about how far away we are going to be. In this case, if I'm taking sample means, it's pretty likely that I would be maybe 3 inches away from the true mean, or maybe even 5 inches. But it's very doubtful that I would be 9 inches away from the true mean. And if I want my X bar to be really close, if I want my X bar to be within 1 inch, then this isn't going to be good enough, because it's not very likely that I'm going to be within 1 inch. Or I mean, there's a bunch of points there, but there's a pretty big chance that I'm not going to be within that. So we might say, well, this isn't a good enough technique for estimating the true mean. I might want to do something a little bit different. You guys probably even know what we would do to get a better estimate. Okay? All right, I'm going to stop this and